right? Sorry for the confusion.
Yeah, no problem. I mean, okay. If you want to talk about time also, then
no.
Okay,
no problem.
Yeah, so Alok, you can start.
Yeah. So, welcome to this session, and good afternoon to those from India, and good morning to today's speaker, Professor Maccone. In fact, I am very happy to get this opportunity to interview. I have met him quite a few times in Patna, 2 times in Patna and 2 times in Bengaluru. And in every occasion, it was really pleasant to meet him. And it is indeed our great pleasure to have Professor Maccone with us today. And we thank him for accepting our invitation and for agreeing to give this lecture. Professor Maccone is currently a professor at Pavia University, Italy. And he obtained his PhD in theoretical physics in 1999 from the same university. And then he had some back and forth motions. He went to MIT for 4 years for a postdoctoral associate with the St. Lloyd's group. And then he came back to Pavia again for 4-year contract position from 2005 to 2008. And again from 2008, he went back to MIT for 1 year. And then for a official guest faculty position at Los Alamos National Laboratories up to 2010. And he came back to Pavia University and he became the associate professor in 2010. Professor Maccone has many pioneering contributions in quantum foundation and quantum information theory, as we know. And in fact, his series of 3 papers on quantum metrology that is published in Nature, Photonics, Science, and PRL, and during his postdoc, actually it gave him a well-deserved recognition in the field. He has made, after that, actually, he made quite a number of very important contributions in almost every aspect in quantum foundations, including this quantum uncertainty relation, quantum clocks, and that are widely appreciated in the physics community. He has published around 150 journal articles, including the Nature, Science, Nature Photonics, IEEE, IEEE on information theory, and there are many more. I would like to mention also that he's among a very few in the scientific community who loves adventure sports. And you can find in his website that the cycling and mountaineering, there are many pictures you can find. So today it is our great opportunity to listen to him. And he will be talking about these 4 postulates of quantum mechanics R3. The title seems mysterious, and such a title of a scientific paper completely fits with his personality. And with this, I would like to invite Professor Lorenzo Maccone to deliver his lecture. Thank you.
Okay, thank you, Alok, for the very nice introduction, very kind invitation. So let me start.
Sure.
You're seeing my screen, right?
Yes.
Great.
But it is full screen, right? So please move 1-2 slides. Let's see how it works.
Okay.
No, it's not moving. Yeah, it moves. Yeah.
Okay, great. So thank you. And yeah, as Alok was saying, this, Professor Pan was saying this is kind of a weird title. The 4 postulates of quantum mechanics are 3. And to give away immediately what this means is that what we showed is that one of the postulates of quantum mechanics is not really a postulate. So instead of having 4, we are down to 3. And this is joint work I did with Gabriele Carcassi and Cristina Aidala when they were visiting here, my group in Pavia. So what am I going to talk about? One of the axioms of quantum mechanics, the axiom that talks about the composite system, the composite system postulate can be actually derived from the other axioms. That's the result we obtained. And this is important because it is a simplification of the formal structure of the theory. When you have a physical theory or a mathematical theory and you reduce the number of axioms, that means you're simplifying the theory. So let me back down one moment. I was asked to give kind of introductory talk. And so let me spend some time explaining what are the axioms in a physical theory. Why do we talk about axioms in physics? So physics is an inductive deductive discipline. What does that mean? It means that you have both an induction stage and a deduction stage, which are different from the logical point of view. So the induction stage is the one that you start from observations and experiments. Experiments are nothing else but controlled observations. Physics is an experimental discipline. So this is the starting point. And then you do an induction step and you get some physical principles. So basically the experiments are done only in very specific situations. So I'm testing the Coulomb law in the physics department of the University of Pavia on June 22, 2021. And then I say, okay, the experiments that I obtain in this very specific situation are valid always. Okay, this is what induction means. I see something in a specific situation and then I say it's always valid. So this is how I get the physical principles. And then the physical principles are formalized mathematically, and there's a logical equivalence between physical principles and postulates, the axioms of the physical theory. So the axioms are just a mathematical formalization of the principles. It's equivalent logically. And then you have the deduction step in which you start from the axioms and then you get all the physical theory. For example, to go back to the electromagnetism, the electromagnetic waves are just some deduction from the physical axioms. Sorry, let me spend a little time on that. So what are the in the electromagnetic theory, which I think everybody is very familiar with, what are the physical principles? They are, for example, the Coulomb law, the superposition principle, the fact that the law of conservation of electrical charges. All these are, there are many more, of course, all these are physical principles. And then you encode all these principles into axioms. What are the axioms in this case? In this case, the axioms are the Maxwell's equations. They are basically, you take all these, the superposition principle gives you linear differential equations, for example. The conservation of charge, you will find it in the fourth equation of Maxwell. The induction principle, you will find it in the third equation, in the second Maxwell equation, and so on and so forth. And so the Maxwell's equations are encode the postulates. In addition to the postulates, of course, you also need the definitions, the definition of electric and magnetic fields, which is given through the Coulomb, through the Lorentz force. So the Lorentz force gives you the definition, and the Maxwell equations give the postulates. And then all the rest of the theory, all the rest of electromagnetism is just a deduction from these principles, these axioms. Indeed, for example, you take the curl of the fourth equation of Maxwell and you get electromagnetic waves, just as an example. So that's part of the theory, which is obtained by mathematical deduction from the theory. Okay, of course, there are different physical ideas that may be equivalent in all their predictions, and then they are scientifically indistinguishable. However, different axioms may not be psychologically equivalent. And and this is a quotation by Richard Feynman. He says, theories of the known, which are described by different physical ideas, may be equivalent in all their predictions and are hence scientifically indistinguishable. However, they are not psychologically identical when trying to move from that base into the unknown. For different views suggest different kinds of modifications which might be made and hence are not equivalent in the hypothesis one generates from them in one's attempt to understand what is not yet understood. I therefore think that a good theoretical physicist today might find it useful to have a wide range of physical viewpoints and mathematical expressions of the same theory, for example, quantum electrodynamics, available to him. What is he saying? He's saying that there might be different set of axioms which give rise to the same physical theory, okay? So the axiom, in mathematics, you kind of tend to keep a fixed set of axioms and then derive the mathematical theories. But in physics, it might be useful, and I fully agree with Feynman on this, to have different set of axioms to describe the same physical theory. Why is it useful? It is useful because a different set of axioms may suggest different ways to approach still unsolved problems, okay, to understand what is not yet understood, in the words of Feynman. So it's true that we can describe the formal structure of a physical theory using axioms, but it's also important when we do physics and not mathematics, it's also important not to crystallize too much on a given set of axioms. So to keep an open mind and to use different ways of describing physics. For example, some formulations of quantum mechanics are more useful for some interpretation. Other formulations of quantum mechanics are more useful for different interpretations of quantum mechanics. Quantum mechanics can be interpreted in very different ways. So, of course, there's a big difference with mathematics. Mathematics is only deductive in the fact that you start from a set of axioms and postulates which you think are interesting by any definition of interesting, and then you deduce the theory, the mathematical theory, just from the axioms. There is no place for induction in mathematics. You do not start from observations. You just have the second part. But physics instead is an experimental science, so you do have also the induction part. So now, of course, we are talking about quantum mechanics, and I'm talking about the formal structure of quantum mechanics. What are the axioms of quantum mechanics? I will point out four different axioms. There, if you take a typical quantum mechanics book, you will find more typically than 4 axioms, but these are the ones that are more important, I would say, and also they are the ones that are sufficient for what I'm going to talk about. So it's a minimal set in a sense. So the first axiom is the axiom about states and observable, which says that the pure state of a system is described by a ray psi corresponding to a set of non-zero vectors psi in a complex Hilbert space. And this refers to the states of this part refers to the states. What is a state? The state is something, a mathematical thing that encodes all the information you have about a system, okay? So what this postulate says is that in quantum mechanics, the state, so the information you have on a system, is encoded in a set of non-zero vectors, which corresponds to a ray, okay, in a complex Hilbert space. Why is it complex? Well, this is just a physical principle. There's a experimental justification of that. There's no deep reason for that, except that you do experiments. For example, you look at the polarization of a photon or the spin of an electron, and you see that real Hilbert space is not sufficient to contain the state space of a photon, of the polarization of a photon or the spin of an electron. You need a complex Hilbert space. It's an experimental fact. So, and also the rest is an experimental fact, although it's not so easy to see it because of the way that the axioms are written, the quantum mechanical axioms are written. The second part of the axiom refers to the observable, and it says that the system of observable properties are described by self-adjoint operators that act on that Hilbert space. So what do I mean by observable property? I mean something that is measurable, anything that you can measure. And what the axiom says is that anything you can measure is described by a self-adjoint operator that acts on this Hilbert space. Now, the second axiom is the Born rule. It refers to measurements in quantum mechanics. This is the most contentious axiom, is the most difficult to digest. So what it says is that the probability that when you do a measurement of some property X, described by the operator with spectral decomposition given by this expression, returns a value X, small x, given that the system is in state psi, is given by the Born rule, which says that the probability of X, given that the state is in system psi, is just basically, well, if you forget about the degeneracy, it's just basically the square modulus of the scalar product between your state and the vector corresponding to the state and the vector corresponding to an eigenstate of your observable. Okay, let's forget the degeneracy, it's not that important. So, first of all, what is a measurement? You have to define what a measurement is. The measurement is an extraction of information from a quantum system. And what this postulate says is that extraction of information from a quantum system is not deterministic, it's probabilistic. This is the probabilistic part of quantum mechanics, so that you do not get information deterministically out of a quantum system, you only get it probabilistically. And this is the rule that you can use to calculate these probabilities starting from the vectors, the states, the rays or vectors, and starting from the observables, which are self-adjoint operators. So you expand the self-adjoint operators into eigenvalues and eigenvectors. You take the vector corresponding to the state, corresponding to the ray, and then you calculate the scalar product. And that's how you calculate the probabilities. Okay, so this is called the Born rule, which is part of the measurement postulate. And of course, now you see how these two postulates come from experiments. So you can perform experiments, whatever quantum measurement, whatever measurement of a quantum system you are describing, you always see that you can get the outcomes in this way. Okay, so these are the first two postulates. And then there is a third postulate, which is which tells you what happens when you have more than one quantum system. Up to now, I've talked about one system and a measurement on that system. What happens if you have more than a single system? And this is the content of the third postulate, which says that the state space of a composite system so if you have more than one, it's just the tensor product of the spaces of the component systems. So you take one system, you take another system to describe this, which will be the state space of these two systems. It will be obtained by taking the Hilbert space for these component systems and then calculating the tensor products of these. Okay. And then you have the last postulate, the last at least of this minimal set. Of course, as I said, you can have many more postulates to describe more specific situation. But the last postulate for the minimal set refers to the Schrödinger equation. So it tells you how the quantum systems evolve. And it says that the time evolution of an isolated system is described by a unitary operator that acts on the vector that represents the system state. So if you have the state psi of the system at time t, this is given by the unitary operator at time t acting on the state psi at time t equals 0, or equivalently by the Schrödinger equation, okay? So you can write this unitary in terms of the exponential of the Hamiltonian, and then you just derive both sides of this equation, and you can get the Schrödinger equation if you prefer the Schrödinger equation. Otherwise, you can just look at unitary operators. Okay, so these are the axioms of quantum mechanics. So I'm talking about rays here rather than vectors. Maybe usually people do not make this distinction too much. What is a ray? So a ray contains all the vectors that have the same direction. So they might have a phase factor in front, and they may have a different length. So array is not, the ray corresponds to normalized vectors, and you do not consider the phase. So if you want to have a visualization of rays, you can think of the density matrices corresponding, the normalized density matrices. So the phase just goes away when you take a ket and multiply it by a bra, the phase goes away. And if you normalize, also the length of the vector becomes irrelevant. Okay, it will be important for what follows that I talk about rays. So the result that I'm going to talk about today is to show that this third postulate really can come from the first two postulates. I'm not going to use the time evolution postulate, but what I will show is that you start from the state and observable postulate and the measurement postulate, and you can derive as a theorem the composite system postulate. Okay, this is what I'm going to show today. You can wonder why I'm not using the time evolution postulate, and the reason is that if you think about this composite system postulate, this is just a kinematical postulate. It's something that pertains to the kinematics of your theory, and while the time evolution refers to the dynamics. So, of course, you don't want to use the dynamics in something which only tells you about kinematics. So this is the reason I'm not going to use the Schrödinger postulate. Of course, as I said, other postulates may be necessary. This is the minimal set of postulates. So where does the tensor product comes from? Well, let's do a historical perspective. So if you look at the traditional textbooks, the ones from the older textbooks, you can you find. For example, the Dirac textbook is the seminal textbook in quantum mechanics. He basically doesn't even talk about the tensor product postulates. He uses some equivalent ones. He talks about the distributive law of the product between states, which is basically equivalent to tensor products, but he does not talk about tensor products. But I mean, Dirac, if you look at his textbook, he's not doing an axiomatic presentation of quantum mechanics, okay? So he's not really presenting the postulates of quantum mechanics. Instead, if you take von Neumann instead, this is another very important textbook, especially from the historic point of view. He is doing an axiomatic presentation. And indeed, he introduces the tensor product postulate. He's one of the first to do so. And the way he does that is, it's interesting because people at that time were used to working with wave functions rather than states, rather than vectors and rays and vectors in Hilbert space. And with wave functions in configuration space, it's a natural choice to join two systems using a product, especially, and I'm going to talk about that later when you look at the law of composition of probabilities. So you just take the product of two probabilities to get the probability of the joint probability of independent events. You just take the product. So in configuration space, taking the tensor product is quite natural choice. So then he explicitly say, okay, let's postulate it in general. So even when we are not working in configuration space, we still should use the tensor product. And of course, if you take more modern textbooks or more modern literature, you will find it indicated as textbooks, as an axiom, this tensor product, especially if you look at the quantum information literature. For example, Wojciech Zurek, he talks about postulate number 0. And I should also mention from a historical point of view that also in quantum logic, there are some results in which people are deriving, in a sense, the tensor product postulate. But if you look at the literature carefully, then you see that they're not really deriving the tensor product postulate from the other postulates. They're adding some more conditions in order to obtain the tensor product postulate. So it's a different derivation to the one I'm going to talk about. What I'm going to show is that it's not a postulate, it's a theorem, because you can logically derive it as a theorem from the other postulates. So of course, some people will say, okay, but there are exceptions to the tensor product postulate. For example, well, I'll talk about the examples. So, and what I'm going to claim is that there are no exceptions, because this is a postulate, so there are no exceptions in your theory for postulates. But for example, when you talk about superselection rules, sometimes people say, okay, this is a case in which the tensor product rule does not apply because, for example, if you have two electrons, you cannot just use a tensor product to join them if you consider these electrons are indistinguishable particles, because, for example, they cannot be in the same state because of the Pauli exclusion principle. But if you think about it a little more carefully, the electrons are not physical systems, right? They are excitation of a field. The field is the physical system. So electrons are states, not systems. They are single excitations of a field. So, and if you think about superselection rules, they are always practical limitations. They are never limitations in principle. And this is actually something that was pointed out many years ago by Haranovs and Susskind in a very nice paper in which they analyze superselection rules. And they really point out that the superselection rules are always practical limitations. So they're not in principle limitations. So the tensor product postulate does not really have any exceptions. So as I was saying, two electrons live in an anti-symmetrized tensor product space, but that is because the electron is not a quantum system, it's a state, it's an excitation of a quantum field. It's a quantum field when you are considering electrons as indistinguishable particles, then it's a quantum field that you should consider as a system and not the electron, of course. Okay, so now let's go a little more into detail about our tensor product theorem. And these are the logical implications that are in our result. So you see the starting point, don't bother, I'm going to describe all these steps in detail later. But for now, let's just focus on the initial point on the final point. As you see, the initial point is just the state postulate and the measurement postulate, like I was saying. In addition, of course, you have to define what you mean by composite systems. And as I will say later, it's the very natural definition of composite system. You just take a set which contains the union of the system 1 and the system 2. So you just use the set union from mathematics, the most natural definition you can think of, composite system, and also you have to define the component system. Okay, so yeah, this is already a little more technical, but let me introduce these notions that I'm going, oh yeah, sorry. And of course, the final point, the arrival point is the tensor product. So you see that you start from these postulates, you start from these definitions, and then you have a chain of logical implications, and the end result of this chain of logical implications is the tensor product. So you see, as I promised, this is a theorem which derives the tensor product rule from the other postulates. Okay? In this sense, I am reducing the number of postulates by 1. So let me say something about these intermediate steps. So we have some properties H1, H2, H3, which are some intermediate results. You start from, well, first of all, I need to introduce a map small m, which is a map which maps the component vectors. So remember that the states are described by rays in a Hilbert space, and the rays correspond to vectors. So the map small m is a map which acts on the vectors. The map large M is a map that acts on the rays, okay? It's a map that takes, the small m is a map that takes the vectors corresponding to the component systems and maps them to the composite, vector. Well, the large M is a map that works on the component rays and maps them on the composite ray. So the small m is a map that maps vectors into vectors. The large M is a map that maps rays into rays. And these various properties, H1 is the property that is the totality of both maps, small m and large m. What do I mean by totality? It means that they are defined on all the states and all the rays. So it's a map that is defined on all of the possible maps. H2 is the property that both these maps are bilinear, okay? And the property H3 is span surjectivity, which just says that the span of the image of the map is the full Hilbert space. So what comes out of the map, that's the span of the image, is the full Hilbert space. Okay? So these are intermediate properties that we will need in order to derive the tensor problem. So let me say a little more about the definition of a composite system. As I was saying, the natural definition is just a set union of the two systems. So I have system A, system B. These are two subsystems, and I want to give a description of them in terms of a composite system C. And as I said, the most natural thing is how do you do? I mean, if you ask anybody, you just take the union of these two systems, and that is the natural way to define a composite system. So it's the composite system is defined by taking A union of A and B, and of course you don't have to introduce anything else. Okay, I'm not putting giraffes or dolphins or anything else in the composite system. Okay, this is how you start from subsystems and you join them. And okay, of course, the opposite way, which you start from the composite system and you divide it into component systems. I mean, the way to go back is a different notion that I'm not going to talk about today. But if you're interested, the way to do it is by looking at which observables you have to define each of the two subsystems, and then you can describe them from these observables. Okay, so what are the main ideas of the proof? I'll just very roughly sketch the proof that talking about. So I start from the postulate A, the postulate of states and observables. And the postulate A is says that all the systems I'm considering, so I'm considering system A, system B, and then I'm considering system C, which is the union of these two, the composite system. From the postulate A, all these three systems have a Hilbert space, and their states can be described by rays. And then I introduce these two maps, which I was telling you before. The map which maps the component vectors of A and B into vectors of C, and the map M, large M, which maps the component rays into the subsystems A and B into the component rays of C. Okay, and now, up to now, I've done nothing except introducing these maps. It's just a definition. I'm just constructing these maps. And now I am going to use the postulate B, which assigns probability. Okay, the postulate B, remember, it's the Born rule, the measurement postulate. And the Born rule says that there is a joint probability. I mean, the Born rule contains the probabilities. So of course, the Born rule tells us about the probabilities. So it must contain all the theory about probabilities. And in particular, we have a theory which contains the joint probability rule. The joint probability tells you that the joint probability of having event A and event B, given some event Z, is given by the probability of having event A given Z times the probability of given B, of the event B given Z and A, okay? This is just a probability that just a rule to join, to calculate the joint probability that you will find in any probability textbook. And since it's in a probability textbook, it means that it's contained in the measurement postulate, because the measurement postulate contains probabilities, and so it contains all the theories we have about probabilities, okay? Now, I'm going to apply this probability in a very specific situation in which I have that one of the two subsystems, let's say subsystem B, the system B is prepared and measured in the same state. So I prepare system B in state B, and then I measure system B in the same state I prepared, okay? It's a very trivial situation, which of course the probability rule just tells me that the probability of obtaining B will just be 1, okay? So for subsystem B, you see that it's trivial. And for subsystem A, instead, I have that the measurement postulate tells me that I have to project the state of system A onto the eigenstate A of the observable that I'm looking at, and then calculate the scalar, the square modulus. So basically what I'm saying is that when one of the systems is an eigenstate of what we're measuring, here system B is an eigenstate of what we're measuring, then the other system is faithfully mapped to the joint system. So I'm looking at the joint probability for the composite system C, and this is just given by the probability of the system A, just because system B is in a trivial situation in which the probability of getting outcome B is 1, okay? So you see that I managed to say something about the probability, the joint probability of system C, the composite system, just by looking at the probability of system A, okay? Using the joint probability rule, okay? This is the basic trick I'm going to use. I'm going to use the joint probability rule to argue that we need tensor products. So this is the main ingredient. So even if you lost me at some point in what I was explaining, let me stress that the main ingredient in this theorem is the joint probability rule. So the reason why in quantum mechanics we use the tensor products is because the probability amplitudes and then probabilities must be joined using products, okay? So this is the main ingredient. Of course, the story, as you will see, is much more complicated than that, but this is the main part. So here, what we are doing is mapping the rays into rays, because this is the map which takes the rays in the system in subsystem A and the ray in subsystem B, and then it maps it into a ray in system C, and then this ray corresponds to a vector in the Hilbert space of system C. C is composite system. And then once you have the vector, which corresponds to this ray, then you use the measurement postulate on system C in order to calculate the square modules, okay? So this is what I'm doing here for system C. This is what I'm doing for system A. And of course, I'm doing it also for system B, but for system B it's trivial because it's just one. Okay, so what I've shown up to now is that M, the map that maps the rays of the component systems to the rays of the composite system, preserves the square of the inner product. So this means that once you have this preservation, you can show that the orthogonality and the hierarchy of subspaces is preserved. Okay, and this is a technical result that you can find in our paper. I'm not going to describe it. But it's important to see that since the square of the inner product is preserved, then of course you can imagine immediately that the orthogonality is preserved, because if two states are orthogonal, then the square of the inner product will be 0, and so also the scalar product will be 0. So the orthogonality is preserved. And the same thing for the hierarchy of subspace. Then M, you can also show that M is collinear, because it preserves the orthogonality and the hierarchy of subspaces, so it is collinear. This is just basically the definition of collinearity. It maps lines into lines, planes into planes, and so on and so forth. Okay, so if you have a plane in the components in the component systems, this map, capital M, is going to take this plane and map it into a plane of the composite system. And then you can use something which is called the fundamental theorem of projective geometry, which says that if you have a collinear map M on the rays, then you can use it to say something about the maps on the vectors. The small m, remember, is a map that maps the vectors of the component Hilbert space into the vectors of the composite Hilbert space. And the fundamental theorem of projective geometry says that to this map, capital M, which works on rays, there corresponds a unique map, small m, that works on vectors, which is either linear or antilinear. And of course, we can exclude the antilinear map. I mean, you can keep the antilinear map. It's just a change of convention. It's just saying, if you want to use an antilinear map, it says that what you're doing is taking the ket vectors of both subsystems and mapping one of the, in the composite system, you're mapping one of the kets into a bra. Okay, so you're just mapping one of the two subsystems, you're mapping it into the dual space. So it's just a change of convention. And it's amusing if you look historically. For example, if you look at the original paper by Schrödinger, in which he derived the Schrödinger equation, he's actually giving the Schrödinger equation for both signs. So he's giving not one Schrödinger equation, but both Schrödinger equations, because he's looking both at the psi and at psi star, because psi and psi star, if you work in configuration space, if you work with the wave function, this is just a mapping to the dual space, okay? So, okay, our theorem actually does not discriminate between linear and antilinear maps, and it's correct that it should not discriminate between these two, because that's just a change of convention. But if we follow the usual convention that is established by now, we discard the antilinear map and just consider the linear map. And then, of course, what I've said up to now just referred to the first subspace. So I'm looking at subsystem A, and I'm keeping subsystem B into a trivial state in which I'm measuring and I'm preparing on the same state. And now I can just repeat the same exact argument for the first subspace. So I prepare the system A into an eigenstate of whatever I'm observing. So now it's the system A, which is trivial. The probability of obtaining result A is 1. And I repeat the whole argument for that case. And then we get a bilinear map. Okay, so if you look at one subsystem, I'm just looking at, I just obtained a linear map in the first system. If I'm preparing and measuring the subsystem B into the same state, then I can only conclude something about the linearity of the map M on the first part, on the first subsystem. Now I repeat the same argument for the second, and I can conclude that the map M, which maps vectors in the component systems into vectors in the composite system, is a bilinear map from subsystem vectors to composite system vectors. Okay, so I've got this argument I've shown you is what is necessary to get the bilinearity. And now, bilinearity by itself is not sufficient. We need to show that the map M is the tensor product. And we can do it in various steps. The step one is we need to show that the basis of the component systems are mapped by this map M into the basis of the composite systems. And then we use the universal property of the tensor product to show that the map M is indeed the tensor product. Okay, what is the universal property? This is something which is the definition of tensor products. So this is something that usually in physics classes you're never shown because it's very ugly. Usually physicists like to think about tensor products as something which has some slots. I mean, it's like something in which you put the vector inside. So my teacher used to say, a tensor product is something with slots. I mean, because he didn't want to go into the mess that is the actual definition using universal properties. And you take this thing which has slots and you put the vector in the space 1 into the first slot. You take the vector in the space 2 in the second slot, and you get the tensor product. But if you want to be rigorous, like we did in our paper, of course, we want to be rigorous about this, then you need to go and take the definition of tensor products, and it's not the only definition you can give, but the usual definition typically is given in terms of universal property. So if you take a Wikipedia page, for example, of tensor products, you're going to find it. And what is this definition? It says that the tensor product is uniquely characterized up to isomorphism. Of course, you can always have isomorphisms, but we don't care about that. By universal property regarding bilinear maps. So given two vector spaces, A and B, notice that here we just have the two spaces. So this is just a Cartesian product. It's just a way to say that we have two spaces. Then the tensor product A and B, A tensor B, okay, so we have a map that starts from the Cartesian product of these two states. So you just start from these two vector spaces A and B, and you obtain the tensor product through this tensor product map, okay? This map, the tensor product has an associated bilinear map T, which is a map which takes the states in the vectors, sorry, in the direct product of in the two states, in the two spaces, and gets a vector in the tensor product space. So you have this map that takes the two vector spaces and gives you a vector in the tensor product space. Factors this tensor product and the associated bilinear map T have the property that any bilinear map M that goes from these from the vector spaces to the tensor product space factors through the map T uniquely, through the tensor product uniquely. That means there exists a unique map I dependent on M, which this map I will depend on M, such that if you compose the tensor product map and the I map, you get M, okay? Which in other words, it means that this diagram commutes. The diagram that takes the tensor product that starts from the two spaces and goes to the tensor product space going through I is equivalent to the map M, which is the bilinear map, which starts from the two vector spaces and just goes into the composite, into the tensor product space. Okay. There's one thing that I wanted to mention is that this universal property by itself cannot be used to derive Hilbert spaces, okay? It is valid in linear vector spaces. We don't need to derive a Hilbert space for the composite system C, okay? We know that the composite system C is a Hilbert space, and we know that because the composite system C is a quantum system, okay? So we can use the first postulate to know that this is going to be a Hilbert space, okay? What we just have to show is that this Hilbert space is the tensor product of two other Hilbert spaces. Okay, so the step 2 I was talking about is to use the universal property to show that this map M, which I introduced using the joint probability, is the tensor product. I've shown you that it's a bilinear map, and then using the universal property, you show that there exists a unique map I, such that if you take these two vectors from the component spaces, this map M is equal to the map I acting on the tensor product. But remember, I've shown you that M maps basis. That was step 1. I've shown you that this map M maps the basis of A and B into a basis of C. So if you start from basis AI and BJ of the spaces A and B, okay, and then you map these bases, you get a basis of the system C, okay? And of course, you can construct bases using tensor products. And of course, also the universal property tells you that these maps correspond to this I map acting on tensor products of bases, okay? So what I've shown you is basically that you can take tensor product of bases of the component spaces and obtain a basis made of tensor products in the composite system. Okay. And this is basically the idea. Oh, of course, I is an isomorphism. So this comes from the universal property. So basically what I'm saying is that M is isomorphic to the tensor product, okay? So I haven't shown you that M is the tensor product. I just shown you that M is isomorphic to the tensor product. And this is physically reasonable because you can always consider, instead of considering a Hilbert space of the composite system, you can always map this to some isomorphic Hilbert space and get the same. Okay, so this was the more technical part. So if you fell asleep, please wake up. These are some nice pictures I put there to wake you up. I put these pictures, by the way, because I wasn't sure I was going to give this talk today because I thought I was talking about something else. And this talk I was originally prepared to for the group of Paolo Zanardi at University of Southern California. And Paolo Zanardi really enjoys ice climbing like I do. So I put these pictures in order to make him envious. But anyways, let's explain now what our result really means. Okay, so let's go back to something a little more light than the technical part I was talking about and try to analyze the physical meaning of our results. First of all, it is well known that the postulates of quantum mechanics are not independent from one another. Okay, usually if you want, in mathematics, you go to great pains to try to get a set of postulates which are completely independent from one another. And also in physics, it would be nice to do that because that makes your theory more essential. But quantum mechanics is not of that form. First of all, our results shows you that one of the postulates can be entirely derived from other postulates. So that shows you that they are not independent. But also before our results, it was well known that, for example, the measurement postulate is largely redundant. Not entirely redundant, but largely redundant. And this is the content of Gleason's theorem. What does Gleason's theorem tell you? It tells you that if you have states described by vectors or by density matrices and observables described by Hermitian operators, by self-adjoint operators, then Gleason's theorem tells you that the probabilities have to take the form of the Born rule. Okay, so the Born rule is not that you can choose something different than from the Born rule to describe probabilities, because Gleason's theorem tells you that's the only choice you have. Okay, so why am I saying that the measurement postulate is largely but not entirely redundant? Because the measurement postulate is not only given by the Born rule. The measurement postulate also tells you that, first of all, you have probabilities when you do a measurement. And this is not trivial. It's entirely not trivial because, for example, in classical mechanics, if you have ideal measurements, you will never get probabilities. So this is the non-trivial part, the content of the measurement postulate. And well, of course, there are also the fact that you the fact that you use scalar product is also part of Gleason's theorem. Yeah, I guess the only non-trivial part of the measurement postulate, non-derived by Gleason's theorem, is to say that measurement outcomes are probabilistic in quantum mechanics. And people, there's a large literature you can find a lot of papers of people that try to use this redundancy of the postulates to try to derive parts of the measurement postulate. For example, Wojciech-Zurek has these very nice, very elegant proofs of the measurement postulate in which he says, okay, let's start from the other postulates, including the tensor product postulates. So be careful. He's using the tensor product postulate. And then he tries to derive the measurement postulate. Why am I saying he tries to derive? Because in my opinion, of course, Wojciech disagrees with that, but in my opinion, he's missing a part. He's missing the part I was talking about before. So he's missing the fact that he assumes that the outcome are probabilistic. And then he derives the form of the probabilities. But there is a hidden assumption in his derivation. And of course, there are also more recent works like this very nice paper by Maccone, Scully, Muller that appeared in Nature Communication a couple of years ago, in which they do something similar. These are very nice results, but they are, in a sense, complementary to ours. So in our case, we are taking the measurement postulate and the state postulate and deriving the tensor product postulate. These people instead are doing the opposite. They are taking the tensor product postulate and the state postulates and deriving the measurement postulate, okay? So all these results, our results, these results, all tells us that quantum mechanics postulates are not independent from one another. And sorry, and this is not very good, okay? From the conceptual point of view, we really don't like that. It would really be nice, also in keeping with what Feynman was saying in the quotation I read before. We don't have to keep the postulates of quantum mechanics fixed. We can think of a different formulation. I'm not aware of any other one which does not use this formulation I've given you in some way or another. But it would be really nice, really nice, to find a way to write postulates in quantum postulates in a way that they are entirely logically independent from one another. Okay, that would be really great. Okay, that's your job. And what we did is, as I was saying, is start from the from the state postulate and the measurement postulate and use it to derive the tensor product. Okay, and as I said during my derivation, what is important, what I want you to remember of all that technical stuff that you can maybe forget. But the important part I want you to remember about our derivation is that tensor products are really very strongly connected to the rule of joint probabilities, okay? You saw how I used the rule of joint probabilities in order to derive our result. So, for example, Wojciech-Zurek, if you look at his papers, he's saying that the tensor product postulate, he's putting it in the non-probabilistic part of quantum mechanics. And that, in my opinion, is not correct, because the only way to really justify the use of tensor products is by using the rule of joint probabilities. So it would be, I mean, it would be great if somebody can tell me, no, look, we use tensor products not because of the joint probabilities, but because of something that has nothing to do with probabilities. I would really love to see that, but I've never seen it in the literature. Okay, as I was saying, okay, of course, the fact that the postulates are not independent is a problem. Okay, so let me go back to the structure of the logical structure of a physical theory I was talking about. So remember, I was saying physics is an inductive deductive discipline because it has both an inductive and a deductive step. And this part really works very well for electrodynamics and for special relativity, in which we do have this structure here I was talking about at the beginning. So for example, we have principles like the Coulomb law for electrodynamics, which corresponds, for example, the Coulomb law corresponds to Maxwell equation number 1, and so on and so forth. And so the principles are obtained by induction from certain experiments, and they are logically equivalent to the axioms, which are Maxwell equations. And then you get the theory, which is electromagnetic wave. Similarly, for special relativity or for general relativity, you have, general relativity is already a little more special, but special relativity is really of this form. You have some observations and some experiments. For example, the Michelson-Morley experiment, which tells us that the speed of light is constant in every inertial reference frame. And then you have basically any experiment, almost any experiment in physics, which tells you that any experiment in physics, almost any experiment in physics tells you that Galilean relativity is a good valid physical principle, so that any inertial reference frame is basically equivalent as far as the physical laws. Okay, and so this is formalized into axioms, and the axioms of special relativity is very simple, basically that the speed of light is a constant of nature. And then you derive all the physical theory, for example, the relativity of simultaneity and all the other. Okay, so for electrodynamics and for special relativity, this logical structure really works very well. But it does not work well, unfortunately, for quantum mechanics. For example, not all the physical principles that you find inside the axioms are directly obtainable from experiments. For example, you have the superposition principle in quantum mechanics, which is formalized as an axiom by saying that the state space is a linear vector space. Okay, the superposition principle translates into linear vector spaces, but it's not really a result of some experiment. Of course, you will say, okay, but when you do quantum interferometry experiments, that is an experiment in which you're testing the superposition principle. You do, for example, a double slit experiment, you see interference fringes, then you see, okay, that's an experiment that is really at the basis of the superposition principle, but be careful, because when you're doing a double slit experiment or any experiment, you cannot do it without doing some sort of measurement at the end. So it also requires the measurement postulate, okay? So you're not just testing the superposition principle, you're at the same time testing also the measurement postulate, the Born rule. You cannot do an experiment that tests only the superposition principle. So it would be really great if we could find a formalization of quantum mechanics that really does that, that really fits into this general framework for physical theories, okay, in which you do that. Quantum mechanics is kind of a mess, also because the axioms, as I was arguing just in the previous slides, the axioms are not independent from one another, and that is not a logical problem, but is certainly very, very inelegant. Okay, so my dream is, let's do it. It would be really great to formalize quantum mechanics using experiments, and that's it. And of course, you can find some sort of similar formalizations of quantum theory that try to do this, like operational constructions of quantum theory. My colleagues here in Pavia really like these kinds of ideas. And I think it's still, this program also, there is this very nice research program by Lucien Hardy at Perimeter Institute, in which he's trying to derive quantum mechanics from operational principles. I'm not sure we are there yet. I'm not sure that their formalizations can really be cast in this kind of framework. Okay, so what we really want is a way to map physics into math, and there are correspondences. So physics is, you talk about states of quantum system. This is just the information you have on a quantum system. I mean, this is, not everybody will agree that states is just the information you have on a system. There are different interpretations of quantum mechanics, and each of them will assign a different meaning to the word state. But in quantum information theory, the most accepted meaning of the word state is information. So the state is equivalent to the information we have. And as I said, when you want to give a mathematical description of that, you go through a ray in a Hilbert space. Then you have measurable quantities and predictions, something you can measure, you can assign a number, a label to. And this, when you give a mathematical description, you formalize that using in the axioms. That becomes a Hermitian operator, a self-adjoint operator. And then, of course, you also have to introduce the Born rule in order to say how you do measurements. Physics, you have composite quantum systems, so you have system A and system B. A composite systems means you take the union, the set union of these two systems. You consider these two systems as a single composite quantum system, and mathematically you formalize that, as I've shown you, using tensor product. And then again, in physics, you have some deterministic reversible evolution. I haven't talked about evolution in my talk because I didn't really need it, but that's a very important part of physics. In quantum physics, the evolution, the time evolution is both deterministic and reversible, and that is formalized using the Schrödinger equation in mathematical terms when you formalize the postulates. And of course, that's equivalent to a unitary evolution. So interpretations, I've talked about interpretations, and of course, quantum mechanics is really very alien theory. By alien, I mean very counterintuitive. So if we really want to understand what quantum mechanics means, we need to introduce some metaphysical baggage. What do I mean by metaphysical? Usually, for physicists, talking about metaphysics literally means something beyond physics, which is not something physical, something that goes beyond physics. And usually physicists don't like these philosophical language. But you really need, okay, you can do quantum mechanics without any metaphysics. You just use a shut up and calculate interpretation, which is, you just don't worry about what any of this means. But if you want to understand it, and that's crucial if you want to go forward in, for example, getting a better theory or joining quantum mechanics with general relativity, or if you really want to understand it, you do need some metaphysical baggage. So interpretation are not really necessary, but they're useful. So in the logical structure of the scheme I was giving you, in addition to all the yellow parts, which is what I was talking about up to now, we also have this green box, which is especially necessary in quantum mechanics. Maybe in other theories it's not necessary, which is the interpretation of what it all means. So you look for a meaning of what the physical theory means, you give an interpretation, and in order to do that, you need some metaphysics, some additional parts. For example, wondering whether the wave function is real or not, represents something real beyond physics or not. And then this dashed line tells us that this is crucial if we really want to go back and try to understand better the theory, try to understand what experiments are necessary in order to do, for example, quantum gravity, to quantize general relativity, then you really need that. If you're just using the shut up and calculate and forget about interpretations, you're not going to be able to do this. By interpretation, of course, I don't intend rules to assign physical quantities to formulas, okay? The rule to assign physical quantities to formulas, that's already encoded into the axioms. By interpretation, I mean what I wrote here. I mean, I want to understand what it really means. Okay, are interpretation only metaphysical? Yes, they are. I mean, by interpretation, I mean a superstructure. For example, in the many worlds interpretation, you add this superstructure of saying, of this universal wave function, for example. But they do, in a sense, smell of physics. Because they, as I was saying, they are a guideline to understanding better what physics means. For example, in many worlds, I was mentioning the universal wave function, the existence of different branches. A person that likes many world interpretation will tell you that the existence of these different branches has testable consequences. So you can design some really weird experiments that nobody has done up to now, and probably nobody will ever do because they are too complicated, in which you are testing quantum mechanics on observers, like the famous Wigner-Friend experiment, in which you are considering a person, an observer, as a quantum system, and you're doing quantum interferometric experiments on that person. Okay? And this, of course, you can work out the details of these kinds of experiments, the Wegener time experiments, and find that this has testable consequences. And of course, Bohmian mechanics will say that the hidden variables, which if you want to recover quantum mechanics from Bohmian mechanics, you must say that the hidden variables are hidden in principle, but really, if you really press a Bohmian mechanics, he will tell you that they are hidden in practice. So Bohmian mechanics is a different theory, not really a different, just an interpretation. If you want Bohmian mechanics to be an interpretation, then you say, okay, the hidden variables are hidden in principle. They are not there. They can never be seen as a matter of principle. But you can say, okay, that's just what the interpretation tells you. But if you say, okay, they're hidden, but that's only a practical limitation, then that's a different theory. It's not quantum mechanics. So as I was saying, this is a very useful to advanced physics as a guide. Okay, I've talked for 1 hour, and so let me conclude. The main message I want to convey is that we have derived what was considered a postulate up to now, the tensor product postulate, starting from 2 other postulates, the state postulates and the measurement postulate of quantum mechanics. And this is, in a sense, the first step for a dream of formalizing quantum mechanics entirely in terms of experimental principles. And of course, byproduct, a nice thing would also be to formalize quantum mechanics in terms of independent axons, not only experimental, but also independent axons. And the take-home message is that we use tensor products in quantum mechanics because of the rule of composition of probabilities of independent events. And this is the paper where we published our result, and this is my email address if you want to ask me questions in addition to what I'm going to take now. Thank you for your attention.
Thank you, Professor Maccone, for a wonderful talk. Actually, Alok has to go for a meeting, so I am taking over. Now the session is open for questions and discussions.
Ms. Panigrahi, can I ask a question to begin?
Yeah.
Yes. Hi, Lorenzo. How are you doing? Yeah, it's good to see you. It was a great talk, and yeah, lots of things to think about. So you mentioned about, the various postulates being derivable. I mean, the idea being that one postulate can be derived from maybe 2 or more others. And so in some sense, that is one of the negatives that you point out in quantum theory. Yes. So how would you go about deriving, for instance, the Born rule?
Oh, okay. So there are many proposals to do that. For example, Wojcik's proposal.
Yes, of course. Yeah. But then that has this circular argument.
Exactly. So in my opinion, well, I actually, when I was working in Los Alamos, I really worked a lot with Wojcik on trying to fix this point. Right. And I failed. So I don't know. Okay. I don't know how to do it.
Yes.
So the point is subtle. So this was pointed out by John Bell in his book Speakable and Unspeakable. So he was saying, okay, we know that we need to take the scalar product, the square modulus of the scalar product of the I mean, basically, you take the square modulus of the wave function, which is the same thing as saying the square modulus of the scalar product of the state times the eigenstate. And you say, we are so, John Bell was saying, we are so used to attaching probabilities to this that we don't even think about it. But if you think about it, you can say, okay, you could have an alternative interpretation of that. For example, the double slit experiment. You are the world expert of that. Indeed, I think Bell was referring exactly to that. Mm-hmm. He was saying, take that, So why should we interpret the fringes as points, probability points in which the photon arrives? Why can't we just interpret these probability fringes, as just an extended glow in which the photon arrives all over the screen, or the electron arrives all over the screen? And this is just, John Bell used these words, extended glow. Okay. The electron is spread out all over the place. Of course, that's not what we see. As an experimentalist, you're going to tell me that's not what we see. No. But if you want to logically derive the postulate, then you're not allowed to use experimental fact. You're just you have to derive it logically from other experimental facts. Okay. So of course, if you and I'm totally fine with that. You say, okay, that's what we see experimentally, so we postulate it, and that's an experimental postulate. Fine. Okay. But if you really want to derive the Born rule, you're not allowed to do that. Okay.
Yeah, that's what I felt.
I don't know how to do that. I don't. Okay. And I think nobody knows, because I've never seen convincing.
Yes, that is indeed, because there's this concept called invariance, which Wojcik came up with, and which was supposed to be this. Yeah, which we sort of showed experimentally and all. But then again, that is used as the basis for deriving Born rule by him. But that has an assumption of symmetry. So it's very difficult to figure out how to do this without any assumptions.
Yes, exactly.
Yeah, exactly. It becomes quite... the second related thing, if I may, this measurement postulate thing you raised, of course, many times, but you talked about the superposition principle and not necessarily being something which you can just, demonstrate in an experiment, again, related to our slit scenario. And the measurement postulate is required. But then isn't that something that will be required? I mean, not just for superposition, but for any other thing that you want to show experimentally, you will need to do a measurement. So
that's a good point. So yeah. I don't know.
I mean, I have an affinity to superposition, Born rule, and measurement. So then, I had to kind of ask you this question. Yeah.
No, of course. Also, the project where
of course, indeed. So, these are intricately connected. So then,
Yes.
So somehow you can't escape this.
I have no idea how one could really do a test of the superposition principle without using a measurement postulate. I don't know. Maybe, as you say, it could be that it might be impossible.
But if you use radio waves, then you can get away without doing intensity measurements. You can measure just the wave function, just the amplitude. Maybe somehow you could talk about superposition without doing the mod square. But then, anyway, we can have a discussion on that in a separate forum. So thanks very much, Lorenzo.
Okay. Thanks for the question.
More questions?
I ask a question, like a couple of comments, Prashanta.
Yeah, please go ahead.
Yeah, sure.
First, Lorenzo, thanks for the stimulating talk. And hello. Am I
you are audible.
Yes, we're hearing you. We're not seeing you, but we are hearing you.
Okay. So the first quick comment related to just the discussion that was around Urboshi's question. So I may point out that also this interesting exercise done by the Valentini, you are perhaps aware, where he shows that if you, in the hidden variable context, if you apply signal locality, then Born's rule, departure from Born rule, implies violation of signal locality. So somehow that's another way of looking at the validity of Born rule being implied by signal locality, the kind of studies that have been done by Valentini. So that's another line of studies within, of course, the hidden variable framework. This is just for completeness, I thought one should mention, because that is also another very deep way of proving Born rule. Yeah, so just that. And now the question that I have, that in the whole discussion of deriving the tensor product, you assume the validity of the postulate 1 for the composite system C as well. So that involves assuming that C is as a Hilbert space and also spectral decomposition for observables in C system. So how is it that one can argue that you have talked so long about vectors and rays in system C and constructing from composite subsystems? What about the observables? That is also an open question. So So how do you address that?
Sorry, I missed, what is that?
So that is an open question that observable in that composite system. For that also you assume the validity of the postulate 1 to derive your tensor product rule.
Yes,
they are valid in the same.
All I'm saying is that when you have a composite system, it is a quantum system. Okay? Well, that's all I'm saying.
Okay.
Then I agree with you that I'm using this assumption. I'm just saying that the composite system is composed by the two systems and it is itself a quantum system.
By itself, quantum system means it's satisfied. You define quantum system in this framework as a system that satisfies
it has a Hilbert space, it has observables, it has states. What you need to show is that these observables are obtained by tensorizing the observables of the components.
Yes.
So, and then you need to show that the states are obtained by tensorizing the states of the component system. But you can assume that the composite system is a quantum system. I mean, without other justification, just because everything is a quantum system.
But tensorizing the observable, that part, where does it come in your argument? Your argument mainly concentrated on
once you tensorize the spaces, then of course also the states and the observables can be written as tensor products.
And so
the important part, which is what I showed, is to show that the Hilbert spaces are tensor products of the component Hilbert spaces. Once you have that, then the vectors can be written as tensor products or sums of tensor products of the vectors, and the observables can be written as tensor product or sums of tensor products of the observables.
Okay, so the spectral decomposition also holds in that sense for the composite system.
Yeah. The spectral decomposition just tells you nothing about the structure. If you're saying that you have a spectral decomposition, it does not tell you whether the spectral decomposition is written in terms of tensor products or not. Okay.
But a kind of completeness of states is assumed, no, in writing the spectral decomposition. The completeness of the states of the eigenstates of the observable, that is assumed.
Yes.
You agree with that?
Yes, indeed.
Yeah. Okay.
Indeed. Well, that's a technical part, but it is important when you define the composite system that you, indeed, in order to avoid problems with the completeness, you have to be careful to, and I mentioned it in my talk, to say that when you define the composite system, it's obtained by the union of A and B and nothing else. Okay, it's important to specify that you don't want to add anything.
That and nothing else means those parts from that complications may come from the completeness of states.
Exactly.
And those
otherwise, you're going to have problems with completeness. But it makes sense physically, because otherwise you don't know what these other things are.
Okay. Thanks.
Okay. Oh, thank you.
Any more questions?
I see one in the chat.
Yeah, please.
Should I read it? For the joint probability of eigenstate B and the state vector A to a composite system, would the inner product be conserved even if we have unitary translation dependent on A? Yes. Not sure I understand the questions, but the unitary transformations, unitary translations preserve the scalar products. So yes, the answer is yes. And indeed, I did not talk about the unitary evolution. I did not talk about the time evolution of the composite system, but thanks to the property you're pointing out in this question, then you can immediately extend what I was talking about also to the time evolution, just because the unitary evolution keeps the scalar products invariant. So the answer is yes.
Okay, so
Prashant, just one quick
please.
non-technical question for Lorenzo, because I noticed that on what was the logo on the right-hand side of your slide? Every slide, the top right corner. I'm used to dolphins. I've seen many. So did you give an explanation? Was that the periodic table or was it?
Maybe it was something from Zoom because
Oh, okay, interesting. Because it was basically
this.
Yes. No, because they always mean something, right?
No, sorry.
Not this time.
It goes away, right?
Oh, it goes away. Okay, so there you go. So then,
it's just a part of my desktop. Sorry.
You just gave an illustration of the measurement postulate. So you just made it go.
No.
Okay, I get it.
I used climbing pictures as a theme for this talk because, as I said, I initially prepared this talk for
the other group. Yeah.
So you see, this is the Matterhorn.
I see. Okay.
And this is a guy who was climbing with us, and we were just in front of the Matterhorn.
So this is your climb towards quantum mechanics, where we can derive everything from experimental observations.
Well, I hope that is much more difficult. Climbing is not as difficult as that.
But it could be metaphorical.
Yes.
Okay. Thanks, Lorenzo.
Thanks.
Yeah, so thanks, Professor Maccone, for a very thought-provoking talk. It will be staying with our mind for for quite some time. Thank you again, and hope to see you here sometime. If you remember, we met in Urboshi's conference in RRI.
Yes. It was a great conference, by the way. Yes.
We are starting to plan. We are starting to plan so that we can converge in 2022 because we are hoping it will be offline.
Oh, yes.
Yeah, a little later on. And we're getting optimistic from now so that we can hold on to our optimism. Yeah.
Great. That's really nice. Great.
Thank you and goodbye.
Thanks. Thank you. Thanks.
Thanks for the invitation. Bye. Bye.